Yeah. So the bottom line of this talk is I will be presenting a method which is basically a match filtering method where you can estimate any hidden signals, any signals of anisotropy underlying a CME stack directly from the master stack. I will elaborate more on this. So yeah. So as you all know, the standard model is based on the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. So if there is no preferred direction or there is a preferred horizon for the universe, all observations regarding our universe will be statistically the same, no matter what your preferred point of, no matter what your vantage point is. So this is the standard cartoon that you might have seen a million times. So basically, the CMB is a probe of very early universe. So it was generated when the universe was only 4 lakh years old. So the current age is expected to be around 14 giga years. So just some jargon. So CMB is a radiation that we are. It's essentially a radiation. It's like a signal on a sphere. We are receiving CMB photons from all directions. So the CMB anisotropies, fluctuations within the CMB's temperature pattern can be expanded or conventionally expanded in terms of what are called spherical harmonic coefficients. And one of the important quantities of interest is the what is called the angular power spectrum (CL), which is basically the modulus square of the coefficients of expansion. So if you have statistical isotropy, then these modes ALMs are essentially various modes of these ALMs are uncorrelated. So if you have isotropy, then the 2-point correlation function essentially depends on the separation between the two angles, two directions that you are looking at, that are of interest, and it does not depend on any specific direction. Either N1 or N2 in the 2-point correlation function. It just depends on the separation between them. And CL is basically the rotational invariant quantity if you have the isotropy holds. So we'll go on to, I will illustrate some signals of isotropy violation seen in CMB data. So this is one of the early signal of isotropy violation seen in CMB on very large angular scales. So they essentially looked at this is called the hemispherical power asymmetry. Like some of the colleagues of David from Oslo did this. So basically, if you compute the power spectrum, the CL that I showed earlier, in different directions, in different hemispheres, centered with respect to the disk centers. So there are like 160. They defined 164 directions on the sky, which are nearly overlapping with each other, and they computed the power spectrum from half of the hemisphere, with centered in that direction. So you find what's called you find the excess power in one hemisphere, which is the dark red region, and in the opposite hemisphere you have a deficit of power. So this deficit is not is at a very significant level compared to the fluctuations expected from isotropic simulation. So in a given realization, you always find some amplitude because it's one realization, but the amplitude is quite at its level of 3 sigma compared to the fluctuations expected from standard model simulation. So it's basically the same thing. So this hemispherical power asymmetry is predominantly dipole in nature. So and it is at the level of 7% at very large angular scales. Amplitude is at the level of 7%, and this is about 3 sigma, inconsistent with the standard model expectations. So the one that I showed earlier is found through data analysis, but then you have this Doppler boosting, our motion through CMB restraint. So this is a guaranteed signal. You cannot avoid this signal. So this will have a model. This leads to this has a isotropy violating. It generates isotropy violating signal at the level of 10 power minus 3. I mean, it's weak, but it still generates. So this is a dominant dipole signal that you see, that you subtract from CMB maps. This is the monopole at 2.73 Kelvin, and this is the dipole that you subtract when you are doing CMB data analysis. But for the first time with PLANCK, it became possible to measure these subtle aberration and modulation effects that will induce at large and at higher. So it was not possible with PLANCK, with metabolism, but it was possible with PLANCK. So this is the effect of aberration and this is the effect of modulation on CMB side. This is exaggerated version of that. So why to bother about isotropy? So it's not some theoretical exercise that we would like to do, but this is one instance of isotropy violation that was seen in WMAP because of the scanning strategy, because of the beam, and coupled with the scanning strategy of the satellite. There was a whopping 3 sigma or 7 sigma, probably 3 sigma level of discrepancy. As I showed, this discrepancy, which is of a quadrupolar in nature. So it is but eventually it was found that it is because of scanning strategy and coupled with beam of the satellite. So another implication is that the dipole anisotropy that I showed earlier, it has when you compute cosmological parameters from different sky directions, it was found that the cosmological parameters also have a mild dipole dependence, which is correlated with the hemispherical power asymmetry. I mean, I can elaborate on that. I will see. So these dipoles for the cosmological parameters are correlated with the dipole axis of the hemispherical power asymmetry. So how can you quantify isotropy? So if you have isotropy, then just CL is sufficient. But if you have anisotropy, then you need a much general basis. So which is called the Bipolar Spherical Harmonics coefficients. So the coefficients are the Bipolar Spherical Harmonics coefficients. So so essentially the isotropy is basically the diagonal, not 0,0 component of this covariance matrix. ALM is essentially proportional to the covariance matrix in harmonic space, if you see here. So okay. So if you have a generalized modulation type of signal in your underlying the CME map, then you can compute the corresponding bipolar BipoSH coefficients. Then they have this generic form where these off-diagonal terms are essentially induced by this generalized modulation field, which otherwise will be 0. So this G is called shape function, just the terminology, and this MLM is the modulation field. So similarly, if you have a Doppler boosting, it will again have has a similar form, but now the isotropy violating field is your dipole field due to boosting, and you have a corresponding shape function. So if you just compare these two forms, then you have a generalized form for any isotropy violating phenomena. So I mean, at least for these two, you know that it is, and it is also true for scalar lensing as well as gravitational wave lensing. It has a similar form. So you can invert this to essentially define an estimator, and you can also find weights using Lagrange multiplier method. And this is how. And if you just apply it to the data, this is the dipole recovered from simulated Doppler boosted maps, and this is the amplitude, the mean, and the injected value agree with each other. But that is not the real sky. So in reality, we don't have sunshine and rainbows. So we have these foregrounds, and you have to do what is called masking, and it is quite ugly. This is the CMB confidence mask, in the sense that the red region is where the PLANCK, this is the PLANCK analysis mask. So where the CMB signal was deemed reliable, and blue region is where they could not trust it. So they have to omit it because the foregrounds will bias your results. So if you have, and this is the work, this is essentially the essence of this work. So basically, if you have masking, then this is the full sky. If you are operating with full sky, then these are the coefficients. But if you have masking, then it takes a very ugly form. So with all this 9J symbols and other stuff. So this is similar. If you are familiar with the master algorithm to recover partial full sky, pseudo full sky CL from partial sky CL, then this is just basically the 0,0 component of this form. But I am not going to scale it more. So basically you have a general form for this isotropy violating fields in a full sky case, but In the modified case, you can just put those things into some symbols, and you have a nearly similar form for if you expand in terms of if you keep only the first order isotropy violating fields. So just like in this full sky case, you can again invert this relation to define your estimator for the field. So basically, you just subtract this bias, which is estimated from simulations, you divide it by that shape function, and you have this expression. I mean, you can use again Lagrange multiplier method, and you can get the appropriate weights. But here you have to notice that the shape function is independent of the M mode. So in the sense that since you are operating on the full sky, then you don't need so all the modes get affected in the same way, M modes. So essentially the shape depends on L. But in the case of masked sky, because the orientation of these YLMs is different, so the different modes get affected differently. So you have to, there is an M dependence in this estimator. Why I mention this is because in the PLANCK 2015 analysis to estimate lensing field, they essentially use a full sky estimator, but correct for a bias term because of masking and other. And also they have to be using very thin mask, because if you use very big mask, then the biases will be large. But these are details, but yeah, I'm not going to show these things. But yeah, so I directly come to results. So that is the estimator that we have. So for the partial sky, so we could recover this. So this has been calculated using the Doppler boost, which is at the level of 10 power minus 3. So so that we are sure that the method works quite well. So this is the amplitude recovery, which is consistent with the injected value, and this is the angle between the injected direction and the recovered directions. So they are the method works quite well. So we applied this method to PLANCK data. So these are the people at IUCAA. I was previously at IUCAA India. So Tarun and Sajid were PLANCK core team members, and Nidhi and myself were postdocs, and he was graduate student on each of us. So as part of this PLANCK, we applied this method to again the lowest hemispherical power asymmetry. So as you can see, the signal is very significant only on large angular scale. So the multipole range L equal to 2 to 64, which is on the very large angular scales. You have a 3 sigma amplitude in consistence with expected lambda CD expectations. And at high L, if you model it as I said, if you model it as a dipole modulation field, it is consistent with random fluctuations up to within 1 sigma. So this is the low L hemispherical direction from WMAP observations, and this is the one that from low L. And it is at the level of 7%, inconsistent with the previous estimates. So similarly, we also recovered the Doppler signal from partial sky using this bipolar mechanism. So we expect 1.23 to 10 power minus 3 at the amplitude, and we also recover the same, and we also recover the direction. So this is a method. We applied this high powered method in some way to just recover the dipole, but this is going to be very important for lensing. So basically, in summary, we developed a match filtering sort of method to recover some form of isotropy violating signal that you have some information about, like a modulation. Maybe there is an underlying modulation field, or operation, or gravitation wave lensing, or so. And this method has been calibrated using the very weak Doppler boosting of CMB anisotropies, and this method was applied to PLANCK data. So this method has to be extended to weak lensing, because the PLANCK 2015 estimate, this essentially uses a full sky estimator, which is obviously which is incorrect, but the biases were compensated in a different way. As you saw, the signal has to be compensated differently for different M modes, different components of the modulation of the underlying isotropy violating field. So even though so what are its implications to model weighting and cosmological parameters? At the moment, temperature data could not shed much light on it, but future polarization data may shed light on it. Thank you.
Question for Pavan?
So if you were to detect this kind of isotropy violation, what kind of order of magnitude would it be? I mean, we know that it cannot be more bigger than the classical CMB perturbation, but would it be a small amount on isotropy, a big amount on anisotropy? What is the...
So we expect to be at the level of temperature anisotropy. In temperature, we see a 7%.
10 to the minus 5?
7%. 7% anisotropy on large angular scales. So if all the density perturbations are sourced from the same source, then you also expect a similar order in power spectrum, in polarization data. But polarization data, the large angular scales are not usable at the moment from PLANCK.
And you're sure that these anisotropies are intrinsic, are not a secondary anisotropy, it's a primary?
These are on large angular scales. So this signal was observed on large angular scales, L equal to 2 to 64. So this is present on very large angular scales. This is not because of secondary effects. Secondary effects are expected higher.
So if you actually find this, our job becomes much more complicated because you have to deal with Yankee models.
Why do you need to wait for new experimental polarization data? Why can't you use PLANCK?
PLANCK on large angular scales, there is some mismatch. There is some leakage or something like that on large angular scales that you cannot use. I mean, in the maps that the PLANCK provides, modes below 20, L equal to 20, are actually removed. So they are not provided as part. So they are not provided at the moment in the current release. So they are already removed. So because the leakage, band pass mismatch, I forgot what's the right term for that. Yeah. So because of these leakages and etc., the uncertainties are not at the level that they are satisfied. That they are satisfied with, I think.
So what experiments are you thinking about when you talk about the future experiments?
So I mean, which are measure the large angular scales, those should be good.
Did you have something in mind, or?
Not at the moment, but Lightbird is coming up, and then even many of the ground-based experiments, they are aiming for large patches of the sky, spider, class. So they might help.
Other questions or comments? Thank you, Pavan, and thanks to all the